Welcome to another part of the ISM course in Statistics 1, this time with a unit on Spearmans Rankcorrelation coefficient. Well, as the name motivates, before we can do anything else, we need to calculate ranks. How are we going about this ranking process? First off, we can apply this method even to ordinally scaled data. We need at least ordinal scaled data because else we cannot get our ranks, but as compared to Pearson's correlation coefficient, Spearman's version can also be used for ordinal data. Well, so we assume we have ordinal data, then our data set can be ordered. The ordered data set would look something like this. We start with x1 being the smallest value, the minimum of the data set, and it goes till xn being the largest, the maximum of the data set. And if we have this, we need to take a critical look at this data set and decide whether so-called ties exist. A tie is if a value exists more than once in this data set. So if our data set starts with 1, 1, 1 and then 2, 3, 8, 17, 19, 58, we actually have ties. And well, we can first start with the simple versions, no ties, and then take a look how ranking works if we actually have those ties. Without ties, it's very easy. We just say, well, each observation is assigned its position in the corresponding ordered data set. So if it is at position I, it gets rank I. So far so good, so no problems here. With ties, we have two possibilities. First off, we can say if we have ties, this means the rank for all values which are similar will also be the same. Then, first possibility, we can say we assign it the smallest or the best possible rank. So in the case we have 1, 1, 1, this would mean all three would be assigned rank 1. So I would have rank 1, 1, 1, and then for the next one, which is actually at the fourth position, would have rank 4. So I would skip like rank 2 and 3, and the first three would all be assigned rank 1. Another possibility would be if I take the mean of the different indices, meaning here position 1, 2, and 3 have the same value. So I take the mean of 1, 2, and 3, which would be 2. So they would all be assigned rank 2. Usually what you use is the first version with the minimum, but the mean version in some cases also is applied. That's why I make the difference here and mention this. So there are those two basic assumptions. Either assign it the best rank for all or assign it the average rank for all relevant observations. Independent of what we have, also for the correlation coefficient, we need to differentiate whether we have ties or we do not have ties. So we can start here with the tie version, which is basically apply Pearson's correlation coefficient to the ranks we actually calculate before with the ranking procedure. So this is just simple repetition of correlation coefficient calculation. So in the upper part, that's the covariance, and below the fraction line, we have the standard deviation for the ranked x variable and the standard deviation for the ranked y variable. So far so good. So this is the version with ties. The big upside is if we do not have ties, we do not need the whole part as seen here. In particular, we do not have to calculate our standard deviations. We can use a simpler formula. And the simpler formula looks like this. Okay, some might say, why is this simpler? Well, we only need the differences between the rank of x and the corresponding rank of y, and we square this. Sum this up, and the rest is just times 6 divided by n times, in parentheses, n squared minus 1. So this will save quite a lot of work, because you only, if you work with a table, only have to calculate one line as compared to 3 or 4 in the upper version. So this will be way easier if you do not have any ties. Well, in some cases it can't be getting around to work with ties, so in this case just apply Pearson's correlation coefficient. However, if you have the lucky situations that you do not have ties, then use the simpler version, because you can save quite a lot of time in the calculation. Well, this then already concludes the short section on Spearmans Rankcorrelation coefficient. We can only give one final remark. As I said, we can use this for ordinal data. This has one downside. This would be, whereas Pearson's correlation coefficient calculates a linear relation, or tests for linear relation, Spearman tests for monotonous relation. So exponential relationships would actually get a relatively large Spearman's correlation coefficient, but possibly a Pearson correlation coefficient relatively small, or small meaning relatively close to 0. So if you want to check whether there might be a positive or monotonous relationship, which however could be nonlinear, you could use Spearman as well on metric data. With this final remark then, we conclude this session. I hope you enjoyed listening to it, and if you're interested in hearing or seeing more of this type of videos, feel free to visit the rest of this playlist and the rest of the corresponding course. I say goodbye, and until next time.